Tak, já vás tady vítám na další přednášce v rámci našeho cyklu. Tento semestr to máme o fundamentálních teoriích, ale přepnu asi hnedka do angličtiny, protože dneska tady budeme mít přednášku v anglickém jazyce. So welcome you here in our next lecture, and I would like to introduce our guest from the France, Simone Speziale, who is actually giving now the course on loop quantum gravity here at the faculty. We just finished one of the fourth lecture, I guess. Yeah, but today he will also present some outreach lecture about concept of this approach to quantizing gravity and general situation around that. He's, as I said, he's from France, from the University of Marseille and Toulouse. If I understand correctly, it is some center of theoretical physics, which is some joint laboratory of these two universities. Yeah. So, welcome and please.
Thank you very much. Can you hear me or is it okay? Yes, perfect. So, thank you very much, Pavel and Tom, for the nice invitation to be here. I'm really enjoying my time. Telling to the students that come to the classes about some technical aspects of loop quantum gravity, but this is not going to be technical at all. This is going to be a talk with no equations and a talk that is going to be, I think, at least at the beginning, very open. Then it might become a little bit more technical, but if it's too technical, we can see how to interact in a more constructive way. Because effectively my goal is to try to open a discussion about some of the conceptual difficulties that are behind this quest for quantum gravity. Loop quantum gravity is a specific approach, it's not the only one, there's plenty. Why there's plenty? Because it's a difficult task, and I will explain why it is difficult. And some of the difficulties of this task have to do with the special features of Einstein's theory of general relativity. Special features that might not be so well known to everyone. So I would like to start this presentation by talking about general relativity, especially because the last 5-6 years have seen the extraordinary successes of this theory increase even more, with certainly things you have heard about, like the discovery, the measurement of gravitational waves, the first pictures of supermassive black holes. So it's a very interesting and active research field, and some of the issues that are manifest in this classical description of gravity are those that then make the problem of quantum gravity complicated. And so I will try to focus on the conceptual aspects, most of it. Now, I said that there is going to be no equations in the talk, and I lied. Here's the first equation of the talk, but if you can see, it's an equation that is so simple that we can actually just write it on some old rusty train. And what is this equation here? It's Einstein's equation. Actually, that form of the equation is wrong. The train wasn't big enough. There's an additional term that has to be added, which is the cosmological constant term, which is needed to explain the expansion of the universe. I will come back to that. Now, even though they're so simple that they can be written on that train, they harbor really the door to some interesting and extraordinary sequence of discoveries that, starting from 1915, have how can I say, entertained the experimentalists and the theorists. These are some of the pictures that I will be talking about, but these are pictures of gravitational waves. This is the picture of the black hole. These are active galactic nuclei, which are powered by the space-time itself. You can extract energy from space-time itself, and that's the only way, as of today, we can explain such super powerful jets. These are the orbits of stars around the central black hole in our galaxy. And this is the cosmic microwave background, which has to do with the Big Bang, which is yet another prediction of general relativity, even though kind of a failed prediction by Einstein, because famously he believed in a static universe, and so he introduced the cosmological constant to kind of have a static universe solution. And so when the discovery of the expansion of the universe was announced, he considered that was the biggest blunder in his life, because he could have actually predicted that the universe was expanding thanks to his theory. How did Einstein make it so far? So philosophy class, so there's a lesson to be learned, and so I would like to tell you a little bit of history, because then we can extract what the lesson is for science. So to put things in perspective, there was this guy in the 19th century that is famous for the prediction of the existence of Neptune. He was computing very precisely, using Newtonian theory, the orbit of Neptune, and he discovered that there were some discrepancies between his calculations and what actually was observed. And so he believed in Newtonian theory, and he predicted that those discrepancies could be explained in case another planet existed, because, you know, in Newtonian theory, you can describe to a very high accuracy the behavior of the bodies in the solar system. A first approximation is just rotation around the sun, but then you have to take into account all the disturbances that are caused by the other planets, Jupiter in first, then Saturn, and you go down in mass. And so, with doing this calculation, you realize that, well, these discrepancies could be explained if another planet existed, and because the theory is deterministic and so precise, he was able to say where the planet would have been, his approximate mass, and so people started looking for them and found it. So that was an extraordinary success of determinism and 19th century physics. Then, in continuing his calculations, he knew that there was another discrepancy that concerned this time Mercury. The discrepancy is this precession of the perihelion, namely when planets go around the sun in the ellipses, the perihelion, which is the closest point to the sun, is not year after year at the same place, but it moves around year after year. And so this could be computed. This moving of the perihelion could be computed using Newtonian theory. And again, there was a discrepancy. So he played the same game. He said it worked once, why shouldn't it work twice? So he predicted the existence of a new planet. This time he named it Vulcan. And he said, guys, go there and fetch it for me. The planet was never found. So the planet was never found because in this case, what was at play was something extremely different. The problem was that so close to the sun, Newtonian theory had reached the limit of its validity and was no longer valid. So the resolution to the discrepancy that he could see was not in the presence of another planet, was in a modification of Newtonian theory. And this is really how science works. This is really how science makes progress. We make some hypotheses, we verify them with experiments, we develop a theory based on these, and then we test the theory until its limits. When the theory breaks down, it doesn't mean that the theory is wrong. It means that the theory had a finite range of validity. And when we go beyond that range, we need some corrections to the theory. And look, there's a very famous example of this. If you are philosophy students, you certainly know a guy named Aristoteles. If you read the physics of Aristoteles, he got F equal ma completely wrong. Aristoteles thought that forces would cause movement, not acceleration. But why did he think that? Because of the observation he was looking at. Observations that were valid in regimes in which typically there's a lot of friction at play and big masses and small forces. Like you have a chariot being pulled by horses. So the horses is struggling continuously just to keep constant velocity. So what you observe is clearly consistent with a force implying a velocity, not an acceleration. It's only by, reducing friction, it's only by reducing the mass involved that people could start finally seeing, Newton, Galileo, that the forces were actually causing an acceleration and not a velocity. So that means that there's a regime of validity of Aristotle theory, which is when friction effects and masses are smaller than the forces. Then Galileo showed that the gravitational force causes an acceleration. And by the way, do you know how he proved it? Because it's really beautiful. Galileo had no algebraic knowledge. There was no calculus, no nothing. What he had was an inclined plane like this with bars. And he observed that at every second, and he was measuring second with his pulse, the position of the rolling ball would be at a different position, and it would always be an odd number. But then he knew something that Pythagoras had proved. And Pythagoras had proved that when the difference is always odd, that means that is the difference of square numbers. And how did Pythagoras prove it? Because look, for Pythagoras, numbers were even numbers are those numbers that you can put in parallel rows, like 6. And odd numbers are those numbers that you can put in the shape of an L. You know, you can always do this with an odd number. And what are the square numbers? Well, square numbers are obviously numbers that you can always put in squares. And so what happens now if you subtract two square numbers, this from that? You see, you always get an odd number. So this is actually how Galileo understood that, you know, the law was a law, of course, then he measured this, but it was a law squared in time by using this type of argument. So this algebraic part of the story is funny, but it's not what really matters. What really matters is that there was a clear understanding of the different regime of validities of the theories, and most importantly, what we learned from Galileo's analysis was the fact that what we should name the scientific method is that we make an hypothesis, we test it against the experiments, and then if it is verified, that hypothesis, we can call it a theory. In nowadays languages, somehow things have completely reversed, and now you hear people saying, well, that's just a theory, as if a theory would be something worse, something bad. But actually, theory is the best we can do about understanding the world around us. A theory means an hypothesis that has been tested by experiments. So it's a positive word. We should, as scientists, as philosophers, we should reclaim the importance of this word and don't let, you know, some people use it in a negative sense, I believe. So the other important lessons that there is to learn here is that Einstein didn't only have this issue of the anomalous perihelion of Mercury to explain. He also had strong theoretical reasons to believe that Newton's theory should be modified. Because in the previous years, he had championed the theory of special relativity, which was a theory that explained how, you know, electromagnetism and these phenomena should be understood in a context in which Galilean relativity was, again, reached its limits of validity, and the limits of validity of Galilean relativity were when the velocities were small with respect to the speed of light. When the velocities approach the speed of light, Galilean relativity doesn't work anymore. We need special relativity. And it's a bit of a misnomer because it wasn't special in the sense that it was more general than Galilean relativity. It was special because it only concerned inertial observers, and he knew already back then that he had to do something about generalizing these to also non-inertial observers. And this would have included the modification of Newtonian gravity, and this is what he also wanted to do. So you see, he had these two friends with him. He had a theoretical reason, and he had experimental evidence that he could have used in order to test whatever hypothesis he would have made motivated by his theoretical reasons. So this is really important, and I will come back to it later on. Now, the new hypothesis that Einstein made based on his theoretical reasons was completely mind-blowing. It was, let's stop thinking of forces as things that act at a distance between bodies that move in space. Let's think of forces as actually, well, not of any forces, but of the gravitational force as actually a manifestation of the curvature of space-time. How can that make sense? Well, there's a simple example that you can think of that will explain how it makes sense. If you consider two rolling balls on this plane, if these balls, there's no force between them, they will stay always at the same distance. Let's assume I've chosen initial condition, they move parallel to one another. But if now one is charged positively and the other one is charged negatively, their trajectories will converge. Now take, instead of this plane, a round sphere, and make the same experiments. The two parallel lines now are two meridians, and you have two balls that roll on these two meridians of the sphere. Even if there are no forces among them, the two balls will touch each other at the north pole of this sphere. So you see that this shows an example in which even though there are no forces, the fact that the movement occurs on a curved space, the sphere, as opposed on a flat space, this plane, creates a change in the relative distance. And so, because of the special properties of the gravitational attraction, specifically the property that the inertial mass is always equal to the gravitational mass, this is the technical aspect, this allowed Einstein to turn this description that I just gave you in a formulation of the gravitational force. This is not true for electromagnetism, because the electromagnetic charge is not the same thing as the inertial mass of a charged particle. So you cannot do the same thing for electromagnetism, even though people tried, following up on Einstein's example. In those days, there was an attempt of geometrifying also electromagnetism, attempt that actually is still nowadays very much alive when you hear about theories of extra dimensions. There's a little bit of that imprint in when people work on extra dimensions, compactified extra dimensions. So of course, it wasn't just the hypothesis. The fact that he was able to realize all of these was thanks to the works of many other people, in particular of mathematicians. They gave him the right language, they gave him the right mathematics in order to make this quantitative, so he could extract numbers from these ideas. And that's what he wanted to do. You know, he was a real physicist. It wasn't so much, okay, he had a very, very deep understanding of the concepts and the physics of the problem, but he wanted to get numbers out of it. So he immediately went and computed the perihelion precession anomaly and got exactly the factor right. That's when he was very happy. But so not only he was happy because he succeeded in addressing the theoretical issue that he wanted to address, namely the limitation of the Newtonian theory, and also he was able to reproduce this number that was this anomaly, and so there was no need of the planet Vulcan that didn't exist anyways, because the discrepancy was explained by the fact that there were corrections to Newton's theory, corrections that could be obtained using the theory of general relativity. What's amazing, though, is that this was tiny, tiny tip of the iceberg, and there were huge amount of consequences that he couldn't figure out, that he couldn't imagine, and that more or less immediately were figured out by himself or by other people. And these are really amazing consequences, which include these gravitational waves, the bending of light by gravity, gravitational time delay, the fact that also the notion of thermodynamic equilibrium changes in the presence of curved spacetimes, black holes, Big Bang, the cosmological expansion, and every single one of these predictions has been confirmed. Actually, not that one, but sorry about that. Well, LIGO observed directly the gravitational waves recently. The light bending was observed, well, maybe that wasn't that quantitative. I think everybody, all historians say that Eddington was a little bit biased in his observations, but still, that's the first instance in which it was a quantitative measurement and he was agreeing with it. Gravitational time delay, you measure it with your GPS every time you use it. This is more subtle effect, and effectively this thermodynamical one has not been observed yet because it's too small. And black holes and everything else, it's very well known. So actually, the real puzzle is not, nowadays the real puzzle is not that these crazy things really exist. The real puzzle is that the fact that these crazy things exist is not part of the popular culture. Because most of them are so old that sometimes, you know, I wonder, I don't know here, but certainly in France, in Italy, where I'm from, these things are not part of the high school curricula. And they should be, because people should know that, you know, time is not something that is universal. People should know that it's not just a subjective thing, like if I'm the one waiting for my girlfriend or if she is the one late at the appointment, we feel time in a very different way. There's actually an objective way in which time is different and runs differently. So let me talk a little bit about these last two big discoveries. So the observation of gravitational waves, this is the one that probably took the longest because Einstein predicted it, I think, if I remember correctly, in 1918, so quickly after it. But it was only observed directly in 2015, so it took a long time. The reason why it took a long time is that they're really hard to see, the gravitational waves. Before saying why they're so hard to see, let me say that people already believed that they existed because there was some indirect evidence. Because already in 74, it was observed that a certain binary pulsar was losing energy, and the only way to explain, the only known way to explain the loss of energy was by emission of gravitational waves, and one could compute how much power was emitted by that particular system, so one could expect how much the system would slow down according to the emission of gravitational waves predicted by general relativity, and that gave that curve, and the points you can see is the measurement. So, you know, if you are an experimentalist and you get such an agreement, you can't be happier. So people already expected the existence of gravitational waves, even though they could not be observed directly for a long time. And that's because they're very, very small. You know, when you think about waves, there's always a notion of, you know, there are two things. There's the amplitude of the wave, there's the frequency of the wave. These things are often related to the rigidity of the material. You know, if I have something very soft and I tapped it with my hand, I will see the perturbation on the material, maybe with my naked eyes. But when I tap on this piece of wood, I can't see the waves. But if you look with a high-frequency camera, you can see that this perturbation has created the little waves on the surface of this table. And if you like seeing it with your proper eyes, there's a YouTube channel that is called the Slow Motion Guys, in which you can see these, for instance, on drum cymbals, and it's really amazing. So the problem with the gravitational waves, if you want, is that space-time is somehow extremely rigid. And therefore, even if you tap it, the perturbance you create is so small that you can't hope to see it. But you produce gravitational waves every time you move. In fact, this is why Einstein wanted to solve the problem of Newton. Newton gave a gravitational description in terms of action at a distance. There was just the Newtonian potential. But if I move this chalk from here to here, the gravitational field produced by the chalk is different, because the chalk was here, now it's there. So in Newton's description, this change of the gravitational potential is instantaneous, and that clearly violates the principle of relativity, that nothing can be faster than the speed of light. So this was the theoretical reason that I mentioned before that Einstein wanted to solve. And so his theory of general relativity better had gravitational waves, because then we resolved the problem of causality precisely in the way that electromagnetism resolved the problem of action at a distance of the Poisson equation. So when I move this chalk from here to here, there's a perturbance, there's a disturbance in the distribution of the gravitational field, whose information is transmitted by a gravitational wave. But it's just too small to be seen. I think in a slide I've written here. You can make this example. So let's forget about my hand. Let's take the Earth. The Earth that goes around the sun produces, in terms of emission of gravitational waves, 200 watts. So you can power, you know, the whole Earth with all its weight going at 30 kilometers a second around the sun. So that's pretty fast. That's a lot of energy you would expect. Produces 200 watts, 4 light bulbs. So you see, it's ridiculously small. That's why it's so hard to see, because it's hard to produce and because they're small in amplitude. But they've been seen thanks to an extraordinary experiment. There's multiple experiments that were able to look at this. And what they actually saw was not the Earth going around the sun, not my hand. You need to go and think about the most immense and strong gravitational phenomenon in order to create strong enough gravitational waves. And that was the bumping of 2 black holes. And since the first one in 2015, plenty of these have been observed. So this observation of gravitational waves is not just a test of gravitational waves per se, it's also a test of the dynamics of black holes. Because the relation between what we observe in terms of gravitational waves and the system that has produced them, we understand it in terms of the theory of Einstein as a coalescence of black holes with certain properties, and so it's also an indirect way of testing the existence of black holes. Now, that's not the only effect. Well, that's also an interesting, if you think about philosophy of science, there's plenty of historians and philosophers that have looked at the history of gravitational waves, because there's a delicate subtlety in the theory of general relativity which makes the description of gravitational waves complicated. And for that reason, Einstein himself was not convinced immediately about the fact that gravitational waves were physical. So it's a long and interesting story, and if you have questions, I'll be happy to discuss it. Anyway, it's one of the most beautiful predictions of general relativity. Another one is the gravitational time delay. So the fact that time slows down the more the gravitational pull felt by the clock is strong. And what is the champion of slowing down time is the black hole. So what hopefully you are already familiar with, and if you're not, I think this is a good time to start thinking about it, is that a clock on Earth ticks at a different speed than a clock in orbit. In fact, a clock here ticks at a different speed than a clock here, because these two clocks are at a different distance between the center of the Earth, and therefore the gravitational pull of the Earth, which decreases as 1 over the distance squared, is weaker here than it is here. It's a very, very small effect. But with atomic clocks, which have a precision of 10 to the minus 16 seconds, you cannot measure this. You can measure this. You can measure the time discrepancy in 1 centimeter. So in fact, this is how people nowadays map the geoid, the shape of the Earth, the differences in the gravitational field, by looking at how atomic clocks tick differently. So actually, if you think about the difference between, and then it's slower on Earth and it's faster in orbit, because the gravitational field is weaker in orbit. Now, if you're in orbit, though, you probably know you cannot just stand static, because otherwise you will be falling. You have to be turning around the Earth in order to be at a fixed distance. But if you're turning around the orbit, then you're also moving, and often you're moving pretty fast. And if you're moving pretty fast, there's another effect that slows down time, which is the fact that you have a certain velocity. This is special relativity. And so that's actually an opposite effect, because if you're in orbit, you're going faster than if you are on the surface of the Earth. And so there's a distance in which the two effects compensate. But when it comes to the satellites that are needed for the GPS, it's the gravitational effect that works. That wins, sorry. So you measure general relativistic effects with your phone every time that you look at the GPS. And of course, with a black hole, if you remember this movie Interstellar, the effect is huge. The people go close to the surface of the black hole for a couple of hours, and the poor guy waiting for them in orbit. Hopefully that's not my girlfriend when I'm late at a meeting, but has to wait for 23 years or something like this. So that effect, so crazy, can only happen through a black hole. On Earth, the effect is a few milliseconds a year. But for the precisions needed for the GPS, that's good enough that if you forget to take that into account, then you will get bad estimates of your location. In fact, the story is that when the GPS was developed by the militaries in the 60s in the US, they didn't believe in such effect. And so they wanted to have the system with and without the GR prediction. And only once they saw that the precision was improving so drastically, they were happy to include it. So nowadays we can say the black holes are really an established aspect of nature, because on top of all the indirect evidence, like no other way of explaining these energetic emissions, planets orbiting around something that is completely dark, stars orbiting around something that is extremely dense, 6 million the solar masses, and completely dark. Now we have also direct evidence, kind of direct evidence, with this picture of the Event Horizon Telescope. I don't know why I wrote EVT, should have been EHT, sorry. Now, it's arguable what this picture really represents, so if you have questions, we can discuss them. But now I would like to move a little bit beyond general relativity and start telling you about what happens when we try to put in what we know about the quantum theory in this gravitational framework. Now, these black holes that we observe, according to the theory of general relativity, they are eternal. They can only grow. So in fact, there's one of the most famous theorems of general relativity. It's a theorem due to Hawking, Stephen Hawking, and it tells you that the area of a black hole can only grow. Now, this theorem is a classical theorem. It assumes that matter behaves classically. So Hawking himself proved later on that if matter has because matter has quantum properties, this theorem has to be modified. And in fact, the quantum properties of matter allow a black hole to evaporate. The black hole will lose mass through a process that is now called Hawking radiation. This process has not been confirmed experimentally yet because it's too hard to measure, but the theoretical evidence in his favor is very, very strong, and therefore the vast majority of physicists believe that this phenomenon occurs, and there's a lot of effort of trying to measure it, not with realistic black holes because it's too small, but with analog systems of black holes, and that's a very interesting research direction. So, in particular, what Hawking showed, so there will be some formula, as you can see in the end, is that there is a temperature associated to a black hole that is inversely proportional to its mass. And so this process of evaporation is going to be stronger and stronger the smaller is the black hole. But if the black hole is big, the temperature is very low and the evaporation is very, very slow. So that's why it's hard to see. Those little pictures are called the Feynman diagrams, and they're supposed to represent the global structure of space-time, and they're useful for this type of discussions, but you don't have to think about them too much. Don't worry about them. So from a standard application of thermodynamics and the presence of this temperature, you can make an estimate of how long it would take for the black hole to evaporate if this process of Hawking radiation continues constantly year after year. And that time is something that is going to be proportional to the mass of the black hole, power cube, the power doesn't matter, but that means again that the more massive the black hole, the longer time it takes. So that's why, again, as before, temperature is too low, the time of evaporation is too long, that's why this effect cannot be measured so easily directly. On the other hand, we might like to ask the theoretical question of what happens at the end of this evaporation. Because the solution of general relativity that describes the black holes has many very, very interesting features. One of them is the fact that time slows the more and more as we approach the event horizon. This glowing picture is not the event horizon, but it's close to it. It's something that is called, it's supposed to represent something that is called the photon ring, which is a surface in which matter falling in can accumulate and turn around the black hole multiple times before being either absorbed or emitted. So the actual event horizon is a little bit smaller, and so you can only estimate its size from that type of picture. This is one of the controversies around the quantitative interpretation of that picture. But anyway, GR tells us, so you see there's this relativity of clocks. So if I'm on Earth, my clock goes slower than somebody that is in space. The same is true if I'm looking at the event horizon, if I'm looking at the black hole from outside, my time is faster than if I'm very close. But it's yet again different if instead of being at a finite distance from the black hole, I'm actually falling into the black hole. If I'm falling into the black hole, my time is completely different from the time of these other two experimenters. And in particular, even though an experimenter that is observing the black hole from a finite distance, fixed finite distance, will observe the person falling in going slower and slower as its own time slows down and never actually reaching this event horizon. For somebody that falls in, the crossing of the event horizon occurs in a finite time. He doesn't feel anything when that happens, and he goes inside the event horizon. What happens inside the event horizon? Experimentally, we don't know. We have no access to it. The theory tells us that there's no way to know it. You either have to go inside yourself and see what happens, or wait until the black hole is completely evaporated and see what it has there at the end. What does the theory tell us? Unfortunately, the theory doesn't tell us much more either, because it tells us that once you enter the black hole, you will hit a point in which the description of space-time stops. You will hit something that is called a singularity. And so this means that the theory stops being predictive. But that's the whole point of physics. I want to give you initial conditions, and then you tell me what the future will be. And by the way, sometimes people hear that determinism, it's lost in physics because of quantum mechanics. That's really bullshit. Determinism is not lost at all. Quantum mechanics is absolutely a predictive theory. What changes, though, is that the only things that you are able to predict are probabilities, amplitudes of probabilities, in fact, and not classical trajectories. So what is changing is not that the theory is less deterministic. What is changing is that your intuition that the world is made of little objects which are well defined, you can touch them, you can hit them, that intuition, which is derived from your senses, which have been selected by natural selection to work at the scales at which they work, have no reason to apply to scales that are completely different. Why should my intuition apply to, atomic scales? Why should it apply to cosmological scales? That's a big extrapolation. That's what is wrong. So to imagine that the electron is a piece of chalk, is a piece of matter, that's what is wrong. But once you understand that the electron is not like that, the electron is a manifestation of some mathematical description that we have, then the switch from classical determinism to quantum determinism, it's easier to appreciate. So These theories are expected to be, I mean, we want them to be predictive, whether they're classical or quantum. We would like that we give initial condition and we're able to predict the future. That's the whole point. And with GR, we cannot do that. We can do that as long as we don't enter the black hole. So then you could say, okay, you know what? Maybe I'm just interested in describing the universe outside black holes. There's billions of black holes out there. But let's imagine that our universe is like, a Swiss cheese. There are all these holes caused by these event horizons of all these black holes, and we are not allowed to know what's inside there unless we actually go in. And so our theory is perfectly predictive in this case. Except that because of Hawking radiation, we know that even these black holes will evaporate eventually, and therefore at some point we will be forced to ask the question, well, we would like to be able to predict what happens at the end of this evaporation. Is the singularity going to be there? Or is the singularity disappeared? And what replaces it? So this is the domain of quantum gravity. Now, we don't have a theory of quantum gravity that can answer these questions. Now, maybe this is a little bit too technical, so there is a perturbative approach, just to tell you, that people agree with, and that's called perturbative quantum gravity. That's something rather consensual, but that's not something that can address these questions. So, to address these questions, what we would like to know is what is actually the quantum structure of spacetime itself. So that's the kind of question that Loop quantum gravity wants to address. Spacetime looks smooth, like in this image here, but this table too looks smooth. And yet, if I zoom, if I look at small scales, it's not smooth anymore. In fact, at some point, it starts being discrete, because it starts being made up of molecules. So it has a discrete structure. And if I zoom in, it gets even crazier, because then I start to see the actual quantum structure of the electrons, and the fact that, each atom is almost empty, but there are only discrete orbits that can be accessed by the electrons. So there are these two natures, these two aspects of the quantum structure of this table, the molecular structure and then the electronic structure. Maybe something like this happens with spacetime too. So maybe spacetime looks smooth, but then at small scales actually has also a quantum nature like this table has. So, but now remember, how did Einstein was able to make so much progress? Because he had those two friends with him. A theoretical reason to do it, and the experimental evidence, this perihelium of anomalous precession of the perihelium that he could use to check his construction. We have our theoretical reasons, I've been trying to argue, because we would like to know what happens at the end of the evaporation of the black hole, or we would like to know what happens if somebody falls into a black hole. But we don't have any experimental evidence. Why don't we have any experimental evidence? Well, because let's go back to this thing of the atoms and the electronic structure. The size at which we can start seeing the electronic structure of an atom, 10 to the minus 10 centimeters, is something that could be accessed experimentally as early as 10, when Rutherford was making his experiments. You remember, I don't know if you have studied this part of history of physics, but people back then did not know how the atom was made. So somebody thought that there was some kind of homogeneous distribution of positive and negative charges, because people knew that there were electrons that could interact, but they also knew that the atom was neutral, so there had to be some balancing. And so there was this panettone model of Thomson. I don't know how you say panettone in Czech. I don't even know how to say it in English. Plan patimone. There you go. You had this model, for instance. And then there was the model of having all the positive charge concentrated in the center and the electrons scattered around. And there was an experiment that could tell the difference apart, because those scales, 10 to the minus 10 centimeters, were accessible experimentally back then. Other quantum properties, photons for the electromagnetic field, those are also accessible experimentally thanks to this. We were discussing it with Tom the other day. But you see, if you want to see the famous duality particle and wave of quantum mechanics, in principle this is enough, because you can shoot this laser through a double slit experiment and you will see the interference pattern on the other side of your experiment that are typical from a wave behavior. But if you're able to control the intensity of this laser and reduce it little by little, because the frequency is fixed, let's say it's monochromatic, then at some point by the uncertainty principle, you will be forced to start emitting photons one by one as you reduce the intensity. And so you will stop seeing this interference pattern, and you will start seeing a single photon hitting either there or there, where you can't predict exactly, but you can predict the probability that will hit there or there. See, theory is still predictive, it's just change of perspective. You are predicting probabilities and not trajectories. But how about the gravitational effects? Gravitational effects are supposed to occur at this scale. 10 to the minus 33 centimeters. So the atom is like 10 to the minus 10 centimeters. The protons, 10 to the minus 12. The Higgs boson, the smallest size we can probe of the quantum vacuum using the LHC. The huge accelerators, 10 to the minus 15. We are immensely far away from that. It's like if I am here and I'm trying to, use my hands to measure, I don't know, the size of a galaxy cluster. So you see, we are really, really far away from experimentally accessing the situations in which quantum gravity will be measurable. So we're missing that friend, and also the theoretical evidence that we have is actually giving headaches. It's not as simple as just the anomaly in the precession of the perihelium. So if you want, not to go into the details, but there are technical challenges in trying to push this lesson forward. And the main the reason why this is difficult is the lesson of quantum mechanics that all dynamical quantities cannot be treated as classical properties, but they are quantum. They have these quantum properties, they can jump, you can only talk about the probabilities, they can be incompatible with one another, like the position and velocity of a particle are incompatible, either you measure one or the other. And the lesson of generativity, which is the spacetime itself, is dynamical. You put these two lessons together, you expect the spacetime itself should not be classical, should be able to jump from one spacetime to another, should have uncompatible properties, meaning that if I know the geometry in one direction, I cannot know the geometry in the other direction, or something like this, and should have quantum properties, like, the geometry of things can only change by a discrete amount, just like this laser can only change by one photon at a time. That's what we might expect. Can we have a theory that does that for us? Or can we have a theory that gives us an alternative picture that explains what the quantum spacetime is? It's a Pandora's box. It's a Pandora's box because it's like super cool question, open out there since 100 years. Nobody has ever figured out the answer. So all the biggest minds, all the biggest egos too, they go into this, and there's lots of ideas and lots of things that have been tried. And there are many, many approaches. These shows loop quantum gravity is one, string theory, asymptotic safety, causal dynamical triangulations, but in fact there's so many more that this is a more representative plan based on different logic in the construction of all the different ideas that have been tried. There's an international society of quantum gravity to try to bring people together and talk about this problem, since it's so hard. It's so hard, but it's by no means wasted time, because in fact, many of the advances in theoretical physics have been obtained thanks to people that were trying to solve this problem. For instance, famously, the way we understand today the strong and weak interactions, the weak interaction is the force that is responsible for some radioactive decays, and the strong interaction is what makes it possible to have the nuclei being charged positively with the electrons being outside. Because, electromagnetism would tell you that this is not possible, these charges should go away. The strong interaction gives stability to that. The theory that describes both these theories is a theory that was developed as a kind of toy model in order to try to understand the problem of quantum gravity. So these type of side results have been enriching the field, unfortunately. So that means that this research has not been completely unproductive. Because from the point of view of answering the initial question we wanted to, no success so far. So let me tell you about the loop quantum gravity approach in itself. How does it work? Again, trying to be not technical. It's an approach that started in the late 80s and the 90s by these three people. And, well, that's a technical motivation, so it's hard to, maybe I can convey it like this. The goal of the approach was to try to really answer directly this question: can I make sense of the space-time geometry as something quantum? So you see, not anymore something classical, fixed, but something with quantum properties. That's what people were trying to make sense of it. And the key technical ingredient that made it possible was a reformulation of Einstein theory that used different variables. This is something that people familiar with quantum mechanics already know. The formulation of quantum mechanics may depend on the language you use, on the variables you use. So for the experts, the fact that changing variables may give you a better handle on the quantum theory is something that shouldn't be too surprising. Concerning the other approaches to quantum gravity, this approach can be considered as more minimalistic, as more humble. There's no grand unification of forces that motivates this approach. And in particular, there are no additional requirements. You might have heard of supersymmetries. You might have heard of extra dimensions. These are properties that we don't observe. These are properties that have been invoked in order to make a certain description of quantum space-time possible, which is string theory, which in itself is, if you want, even a nice idea, dating back to the early 70s, in fact, in its original formulation. But it unfortunately stumbles against difficulties which, in order to solve, you need to invoke these additional features that we don't observe. So the advantage of loop quantum gravity is that we don't need to assume all this extra baggage for which there's no experimental evidence. The disadvantage is that we end up having a language that is quite different from the language of quantum mechanics, and that makes it hard to interpret the theory. That makes it hard to understand how to extract predictions from the theory. So don't get me wrong, there are no predictions that can be made of loop quantum gravity as of yet. There's one potential prediction if you want, but I will describe why it's not really a prediction. So let me tell you in simple terms how this theory describes quantum space-time. This will be better appreciated if you know a little bit of quantum theory. So quantum theory of any field, be it the field of the electron, be it the field of the electromagnetism, it's always characterized in terms of something that we call the Fock space, and the quantum states describe the number of particles. This can be the number of photons, can be the number of electrons, and then certain properties that this particle can have, which we interpret as momentum, namely the energy and the velocity that this particle have, and the helicity. The helicity is something that you can think of as the particle spinning, but it's not really the particle spinning, but it's something related to, if you remember the structure of the atom, you remember that on each orbital you can put 2 electrons, not just one, if they have opposite spin. So that spin is what I'm calling here helicity. It's the same thing. So we could just call it spin instead of helicity. In loop quantum gravity, on the other hand, this picture is replaced by a relational picture in which the states are labeled by a graph. This gamma stands for a graph, something like this. And this graph, it replaces the number of particles. So if you want the Fock space description, you remove these edges and you only have the nodes, which represent the particles. But here this graph is not embedded in space-time. This graph is abstract. This graph is supposed to tell you how space-time emerges. Just like you have a collection of photons, and that tells you how an electromagnetic wave will emerge. Or if you have a collection of electrons, and that will tell you how, electrons and protons, how this table will emerge. This is a collection of atoms of space from which you are supposed to reconstruct space-time. And this graph is decorated by labels which are the analog of momentum and helicity, and these labels are attached to the edges and to the nodes or vertices of this graph. And what is the interpretation of these labels? These tell you the energy and momentum of the particle. This tells you its spin. Those labels are to be interpreted as telling you how space-time emerges from this picture. So in particular, if you cut this edge with an arbitrary surface that is intersecting that edge, an abstract surface. This surface will pick up a quantum of area. So you see, just like there's a quantum of electromagnetic field, now there's going to be a quantum of space-time, because the gravitational field is the same thing as space-time. This is what Einstein taught us. So a quantum of gravitational field means a quantum of space-time. And in particular, this will be the spectrum. But anyway, it's a formula. Forget about the formula. But it shows this number is an half integer, unlike p, which is a continuous label. So this spectrum is going to be discrete, like the energy levels of the electron. Here we find that the areas are discrete. So we can answer one of those questions that we had. If we can make sense of quantum spacetime, is it going to be continuous or discrete? According to this theory, it's going to be discrete. There are only little jumps of area that you can add one at a time. And how about the other quantum number? Well, the other quantum number associated with the node tells us about a chunk of volume, contribution of volume. So this is, okay, if you know about black hole entropy, this is very relevant for understanding black hole entropy, but if you don't, it doesn't matter. The problem, though, is that you can say that this is a prediction of the theory. The theory effectively tells us that at the Planck scale, space is discrete, as quantum jumps. So you might think that that's a prediction, but you can't really say that, because there's no way to... So how can you make this operational? At those scales, we have no idea of how matter behaves. So there's no way that I can say that I can delimitate a surface. You know, if I want to tell you that the area of this piece of paper is discretized, I would be lying, because you see that the piece of paper is characterized by a border which fluctuates on scales which are much bigger than that scale. You see what I'm saying? So that you cannot really take it as a prediction. If you want, it's a theoretical prediction, but it doesn't have an operational consequence yet. So what people do is to look for indirect consequences, namely consequences that could occur for astrophysical problems like the evaporation of black hole or Big Bang due to such a discrete structure. And just like I was mentioning that there are different aspects of discreteness here, there's the different levels that the electron cannot be in an arbitrary distance, can only be at finite distances, and it cannot have more than 2 electrons on each orbitals. And if you measure its velocity, you don't know its position. There are these different aspects of quantum structure. In this quantum spacetime, there's also different aspects of quantum structure. There's this discreteness of the spectra, like this, and that's captured by the example I just gave you. The area, the minimal quantum of area is discrete and increases by minimal number. There's also a non-commutativity, like the non-commutativity between position and velocity, which means that at certain scales, you cannot measure different properties of the geometry. And there is the discreteness associated with the graph structure, which is kind of the equivalent of the molecular structure in the example of the table. So if you want, you can think of such a quantum geometry. I told you that each node gave you a notion of discrete volume. Each edge gave you a notion of area shared by the different chunks of volume. So you can picture this as some collection of polyhedra attached to one another according to the relational system that the graph tells you, and that the volume of the polyhedra is discretized and determined by those quantum labels, and the areas are discretized, except that this picture would be wrong in just the same way as saying that the electron spins with h bar over 2 angular momentum is wrong. It isn't spinning like that. It would be spinning faster than the speed of light if it were. Well, no, the electron, no, there's no problem because it's point. But anyways, it's not really spinning. That's just an image that we have. Here too, these are not really polyhedra because of this non-commutativity of the geometry. So some of the properties that you would need to classify polyhedra and determine their geometries are incompatible with one another, just like X and P. So it's a fuzzy collection of polyhedra, if you want. So there's discreteness, there's fuzziness, and there's this finite number of particles. And finite number of particles is there where we are kind of stuck, where the problem is. Because with a finite number of particles, you can still predict a lot of experiments. You can predict a lot of physics. You can do experiments to test your predictions. But with a finite number of atoms of space, you are infinitely far away from our scales. So if you want to make predictions with this theory, you need to find a way, theoretical, numerical, approximation, whatever you want, to be able to describe an humongous amount of atoms of space so that you can actually talk about the large scales with respect to this ridiculous number that we can access experimentally. And that's the difficulty. So if you want, if you're expert in quantum field theory, you might understand why this difficulty, because, you know, treating computing Feynman diagrams in which you have, I don't know, 10 to the 50 external particles, it's something completely implausible. The number of Feynman diagrams you would have to compute, it's just meaninglessly much bigger than the number of the atoms in the universe. So we need, what is this? Oh man, I forgot this animation. Well, these are just technical ideas that people are working on. So for the experts, we have an analog of Feynman diagrams, and these are called spin foams for the expert in quantum field theory. That's how we try to do the calculations, and we can do them, but this is the problem that we will need in order to have predictions to treat a very, very large number, and we don't know how to. So for that reason, what people have been, once the basics of the theory were solid enough, people have been actually focusing on a less ambitious goal. Instead of trying to get prediction directly out of the theory because it looks so hard, let us look at simpler systems, and let us see if we can, for this simpler system, deduce some physical consequences that would occur because of such a discreteness of space-time. For instance, our motivational questions were like the singularity. But the singularity occurs even if you take the simplest of all black holes, just a spherically symmetric black hole, is described by a single quantity, which is one line element of the metric. So then maybe you can try to do some kind of, you know, Born-Oppenheimer approximation. You say there are some degrees of freedom that I'm interested in, for which I apply quantum mechanics, and the other degrees of freedom I treat them as a classical observer, and I don't quantize them, and I may still be able to describe the physics of what is going on. For instance, to describe this physics, you don't need to quantize the electromagnetic field. So maybe we can content of quantizing just the single scale factor of the universe or the single scale factor of the black hole, and understand if there is a singularity resolution that follows from the input of loop quantum gravity in this toy model. So that's what it's called mini superspace models. You ignore the extraordinary complexity of the gravitational field, its infinitely many degrees of freedom, and you focus on a finite number of degrees of freedom, and you try to see what you can learn for these models. So by construction, you're not looking at the full theory anymore. You're taking a different theory, this mini superspace model, and making some input, some hypotheses there. But this gives rise to a very interesting phenomenology. This gives rise to very interesting physical consequences, which, even though they cannot be considered as direct predictions of the theory, it's very interesting to discuss and motivate further developments of the theory to make the relation between this mini superspace and the full theory more consistent, more concrete. So how much time do I have to talk a little bit about this? 30 seconds or 30 minutes?
30, up to 30 minutes.
Ah, okay, 30 minutes. No, I won't need all that much time. Okay, great. Yeah, okay, good. No, I won't need that much time. 10 minutes more, it should be fine. I was afraid of being late. Okay, no, that's good. Okay, so first example is cosmological setting. So this singularity that I mentioned is hidden behind the event horizon in the case of a black hole. It's actually not hidden at all in the case of the universe. Because if you retrace the evolution of the universe back in time using Einstein's equations, we discover that at some point the universe was very, very small, very, very concentrated. The density of energy was huge. It was very, very hot. And if we keep tracing this back in time, we reach a moment that is called the moment of the cosmic microwave background radiation, this hot Big Bang that we can observe when we take pictures of the farthest distances that we can observe. And we cannot see any further than that. So that's where the experiments, in a sense, stop, because you cannot take pictures before that. But with the theory, we can go even beyond that and earlier in time. And if we do that, just using the Einstein's equations, again, we have a problem of lack of predictability. This is lack of predictability going back in time, but that doesn't matter, because the laws of physics are always invertible. Time arrow, you know, the arrow of time is just a statistical consequences. It's the fact that you give some approximate coarse-grained description of the universe you observe through your brain. But there's no arrow of time in the fundamental laws of physics. You can always evolve back or forth. You know, the only difference is that, you know, the initial conditions are different, and that's what gives you. There are many, many initial conditions that give rise to a similar evolution, and when you go back, very only special conditions will give what you see earlier on, and this gives you the illusion that there's an arrow of time. But it's just due to your coarse-grained description. So we can talk about predictability also when we go back in time. And again, we lose predictability because the Einstein's equations tell us that at some point, all the matter were concentrated in a point in which there was a singularity, and we don't know what happens after that. Again, loss of predictability. So we expect to have a theory which tells us what happens instead of this demise of the field equations of Einstein. And so that theory is loop quantum cosmology, which is something that is motivated by loop quantum gravity. The problem is that if you do this mini superspace approximation, you lose structures because you're losing infinitely many degrees of freedom. So you lose those structures that allowed you to derive the discreteness of the quantum geometry in the first place. So what people do is, okay, so how can I have the cake and eat it too, as they say in English? Well, let me do the symmetry reduction. Now I don't have a derivation of the discreteness, but I put it by hand. I put by hand the discreteness because I hope that the symmetry reduction can be consistently derived from the full theory, and the full theory has such a discreteness in itself. So let me put in the discreteness by hand. You do this, and you discover that the Friedman equation, which is the one written in black, it's modified. It's modified by a term that behaves like some effective quantum pressure. Similar to some picture that people had at the beginning of the century, the stability of the atom, how come the electrons don't fall on the positive? You know, by classical electromagnetism, this thing doesn't exist because, you know, the electron spins around the nuclei, it radiates, so it loses energy, and it falls into the atom. So by classical physics, atoms don't exist. Our universe doesn't exist. So quantum mechanics is absolutely necessary to explain the universe that we observe. So there's some quantum repulsion that at some point prevents, if you want, you can intuitively think in terms of quantum repulsion that prevents this electron from falling into the black hole, into the nuclei. So that's what you get here too. There's some, that rho Planck is some constant that takes into account the energy version of this scale. This is a length scale, it's called the Planck scale. There's an energy density version of it, which is called the Planck density. And when the matter has been concentrated so much by this collapsing, reverse collapsing of the universe towards earlier and earlier times, higher and higher energies, smaller and smaller sizes, when this happens, rho grows, and so this term, which is a large scale negligible because this number is huge, now this grows, at some point this term becomes important, and it changes the behavior of the scale factor, which instead of keep decreasing, stops, reaches a minimum, and starts increasing again. So the Big Bang is replaced by a big bounce, by which the evolution of the universe, oh no, I have a picture, I don't have to draw it. So the evolution of the universe, going back in time, instead of continuing towards the singularity, at some point it bounces back. And so in this simple scenario, mini superspace model, no infinite degrees of freedom, no gravitational waves, you get a picture like this, in which there was our universe comes from a previous universe that was collapsing. And so you can imagine that according to, if you put in the right amount of matter, you might restore Einstein's dream of a static universe, except that instead of being static, is now periodic. It's a universe that has, big size, then shrinks back to a minimal size, bounces, goes again, and so on. A cyclic universe. To be fair, loop quantum cosmology is not the only theoretical exploration that predicts such a cyclic universe. There are others. So this is an idea that has been around for quite some time. In loop quantum cosmology, it emerges naturally in this type of models. Then you can ask, this is how, okay, doesn't matter. Now there's a beautiful mathematical theorem, though, that tells you that you cannot trust really this result in the full theory. It's a mathematical theorem, but it's very solid and it should be taken seriously, which is the fact that you cannot expect that if you have quantized the symmetry-reduced model, this corresponds to the symmetry reduction of the full quantized theory. So that's why we cannot claim that such a bounce is a prediction of loop quantum gravity, because it's not. It's a prediction of a certain model based on an input from loop quantum gravity. If you want to get predictions from loop quantum gravity, we have to work harder. And now maybe one thing we can try to do is to look at the problem of black holes. Now you can look at the problem of black holes also as a mini superspace model, because again, you can take a spherically symmetric black hole, for instance, or an axially symmetric black hole. And then this again reduces the problem to a finite number of degrees of freedom, and then you can take the input of discreteness from loop quantum gravity and see what happens. And people do this, and what they obtain is a similar picture in which there is a bounce. So the person that falls into the black hole will at some point, if he's able to survive the energy densities of those scales, at some point will bounce again into a new universe on the other side of the black hole. That's the picture that emerges from applying the same mathematical technique to the description of black holes. Now this type of picture, again, is not unique to loop quantum gravity or black holes based on loop quantum gravity. There's in fact a whole branch of theoretical physics that is based on studying non-singular black holes, right? Because this black hole is kind of the central arena to play with quantum gravity ideas. And therefore, there are many approaches and many different research groups that describe such regular black holes, or non-singular, synonymous of the two. So if you know a little bit about how the structure of a black hole works, you know that the causal structure is dynamical, so the light cones, which are fixed in special relativity, can bend, can change shape in general relativity, and in particular what happens in a black hole is that there is a region, the event horizon, in which the light cones get completely tilted, so the time and space flip their roles, and you cannot escape the black hole anymore. You're forced to go inward, and you will fall into the singularity. In these singularity-free models, there is a second magical surface here, which flips back the light cones, and therefore once you pass the surface, now you can move, you don't have to hit the singularity anymore, which is, by the way, not a singularity anymore anyways, because the model is regular, and that's how you can tunnel, you can go into another universe. Now, if this is the model that is correctly capturing the physics, what we should do is to ask the question, okay, then what does this model tell us about the end of the evaporation of the black hole? And you cannot really do explicit calculations, because these are nonlinear calculations in a dynamical background. We don't know how to do them. But you can try to extrapolate from the calculations you can do the results that you could expect. And the result that you could expect is that as the event horizon shrinks, maybe I should explain this, but the size of the event horizon of a black hole is associated with the mass of the black hole. So it's squared. So the area of the event horizon is proportional to the mass squared. That's why the bigger the black hole, the bigger its event horizon. That's why the Event Horizon Telescope doesn't try to look at small solar mass black holes in our galaxy because they're too small. They look at the supermassive black hole in the center of our galaxies or other galaxies because they're much bigger. So when Hawking radiation takes away mass from the black hole also shrinks. So this event horizon shrinks. And what you can deduce in these models is that this internal horizon, on the other hand, will increase in size, so that the two will meet at some point, and this point P where they meet, that's the end of the evaporation process. So then you can ask the question of what happens then to everything that went inside the black hole. If there is no singularity, then everything is still safe. Well, it's still safe except that this internal horizon acts also as a special property, just like the event horizon has the special property that you cannot pass through it in one way, but only in the other. This internal horizon has the property that acts as an accumulation surface. So everything that bounces back from inside the black hole will accumulate on this surface here, and therefore will be released all at once when the evaporation is completed. And this is incompatible with energy conservation. So these models, although, as I said, this is not an explicit calculation, these deductions that people do based on the calculations that they can do, these models seem to have a problem with this accumulation. And so this led to consider alternative scenarios, and one very intriguing scenario that was proposed by Carlo Rovelli, one of the founders of this theory of quantum gravity, is that maybe what happens is that even before the evaporation is complete, the black hole is so small that another quantum effect can take place. So I've told you about the quantum effect that gives you these fixed distances, that gives you only 2 electrons per orbit. There's another quantum effect that is very interesting, which is tunneling. You know, I cannot walk through the wall, but an electron can. There's a finite probability that an electron can pass through that wall. And the only reason why I cannot pass through that wall is that you would require, because I'm made of electrons, so, and protons and everything else, so every single one of my electrons has a probability of tunneling. But for me to tunnel through, you would require that this event, this highly improbable event, occurs simultaneously for all the electrons of my body, so to speak. So you see why I cannot go through. I will have to be, you know, the 10 to the 23 atoms in my body will have to tunnel simultaneously in the same directions. That's why it doesn't occur. Not because it's impossible, just because it's highly, highly improbable. So this effect, quantum tunneling, could also be at play in quantum gravity. And so his idea is that there's a quantum tunneling between this black hole solution and a bouncing, time-reversed solution, which is called a white hole solution. So maybe it is possible to do explicit calculation to test this idea. And now I have a big formula for you. So that's trying to make loop quantum gravity predictive, namely trying to use the full theory to verify such an idea. Because this is something that you can try to test. You can set up a quantum state that approximately describes the collapsing black hole and approximately describes the exploding black hole, and then trying to compute a quantum tunneling amplitude. But there are problems. Problem is that, first of all, we can write the formula, it's well defined, we don't know how to evaluate it. We don't have good approximation schemes that we know how to use. For reasons that I explained during my class, because the usual approximation schemes are based on, you know, expansion in energy, expansion in velocities, and things that like these are difficult to characterize in this type of approach. So we don't have a good, even though it's well defined, we don't know how to evaluate it explicitly. But furthermore, as I said, there are approximations going into this. We approximate initial states, and we truncate the amplitude. And we don't know, because we don't know how to evaluate it explicitly, we don't know how bad these approximations are. So we're not at the point yet in which we can make predictions, even though it's kind of an idea of how we could, in principle, do it. So let me conclude. So low quantum gravity has some very nice features. Namely, it presents us with a picture of what could be a description of quantum spacetime. I'm saying what could be because we have no experimental evidence that confirms that this is actually what is going on. There's some theoretical evidence based on hypotheses. Every theory is based on hypotheses. So we cannot say that it's true because we have a theory for it. Because, you know, it's based on hypotheses that we cannot verify yet. But the mathematics of it, the conceptual framework of it, has some compelling features, which makes it so that there's about 300 people, most optimistically speaking, in the world that work on this. That's not enough to make the progress that we need to solve the problems that haven't allowed us to make predictions yet. So hopefully, maybe some of you will join this effort and come with new ideas or new techniques in order for the required progress to be accessible. Symmetry-reduced models have produced a lot of interesting possible outcomes. And so in outreach talks, people often talk about these big bounds and exploding black holes, which is very interesting, but has limitations and what I was saying. And so more work is needed. And maybe the future breakthrough will come from, you know, putting together ideas from these different approaches that exist. And I think it's a good time to stop. Thank you.
Okay, thank you very much. I think that we have time for some questions, and I take actually advantage of the microphone which I have, so I will ask first about this picture, what you have there about bouncing universe. Yeah, you also mentioned that we have observation of asymmetry of time in our universe, and that this asymmetry is related to difference between initial and final condition. So how I should understand this joining of two universes? Is it initial condition on both sides, or?
It's a very difficult question. It's a very good question that researchers are actively working on it, not me. So my answer has to be taken with the benefit of the doubt of a non-expert. Certainly one of the things that people are interested in is precisely to understand how natural are the initial conditions that would create this. Because if there's only a very special set of initial conditions that gives rise to this, there cannot be a plausible explanation. So one of the key problems is precisely making sure that this occurs for general enough initial conditions. And I should look at the paper to give a more precise answer. But it is clearly one of the key questions, as it is the immediately related question of what the hell is then going on with the entropy here. Is entropy in the previous universe supposed to be decreasing, or was it still increasing and then it just resets to zero? So this is a problem that every cyclic universe has. For instance, one of the cyclic universes is called the ekpyrotic universe, but another one, it's a very beautiful idea of Penrose, of the eons. And if I remember correctly, his logic is that simply resets the entropy, so it's always increasing. But when you do this conformal compactification of the new eon, you reset the value of the energy of the entropy to zero. But these are precisely the kind of tricky questions that these scenarios brings in fact.
Okay, some questions?
How do you get dynamics in loop quantum gravity?
Right, very good. So I kind of skimmed over that, but that's exactly one of the problem, in the sense that how do we we have these atoms here, these electrons, how do we know because they're there? Because we have the dynamics that is given by the quantized Coulomb equation. How do we know that the molecules are together? Because we have the dynamics that once again is given by the Hartree-Fock equation. So we have this picture of this polyhedra, the fuzzy polyhedra, which at the Planck scale we know are articulated in a relational way given by the graph. But why is it difficult to reconstruct a smooth spacetime out of this? Because we need to know what is the interactions that governs these atoms of space. And these interactions should be such that, reproduces not just a smooth spacetime at a large scale, but a smooth spacetime governed by the Einstein's equations. Because here, when you go a large radius, you recover the classical Coulomb field. Otherwise, nobody would have believed this quantization. In the limit h bar going to 0, you want to recover classical physics, so we want to recover the Einstein's equations. And yet, at very high energies, very short scales, we can afford for deviations from the Einstein's equations. This is the key question of dynamics. And as I was saying, it's very complicated. There are various technical reasons for which it's complicated. And people use different approaches to study it. So please come to my class next week, because I will say a little bit about how people try to describe the dynamics of this quanta of space. One way is this. Actually, this is for many years I've worked on this way of describing the quantum dynamics, which is the low quantum gravity version of Feynman diagrams. The problem with that, as I said, is that it's very tailored to describe what happens at the Planck scale, but it's hard to then discuss large scales with this. But please come next week and I'll tell you more.
Next question. So maybe I will...
Don't be shy, eh? I'll be happy to discuss whatever you found interesting or confusing or unclear.
Yeah. I will ask actually a question which is properly related to this question of dynamics, so you probably, again, will not answer fully. But you described these atoms of space, these basic states which are described by graph and some labeling. Yeah, but these are not state of our universe. Yeah, our universe will be some huge superposition of these elementary states. Yeah, so do we have some access to this superposition which would correspond to the classical geometry?
This again answer a little bit more, because it doesn't involve the dynamics necessarily, because you might ask the question at the kinematical level without following the Einstein's equations. Can I just have a reconstruction of a classical spacetime? And you see there are these three aspects that you have to take into account. So you want to find the classical limit at all three levels. So you want to not see anymore the discreteness. That's exactly what I described here. You go to large n, where n is the quantum number that tells you the radius. In the limit of large n, you recover the Coulombic orbits, or if you want Newtonian orbits for the hydrogen atom. So the first thing you want to do is large quantum numbers, like in quantum mechanics. Large quantum numbers, it's the first step. You want to recover some classical behavior. But then you have the non-commutativity of observables, which means that, some observations may be completely fuzzy even in the limit of large quantum numbers if you use pure states. If you use certain eigenstates. So the solution to that in quantum mechanics is to use a special set of states, which is called coherent states. For instance, if you want to describe the trajectory of a particle, you will not use an eigenstate of the position or the energy or the momentum. It would be a bad idea. You would use a coherent state. So these two things we know how to do quite well, but that's yet not enough. What you also want to do is to increase the number of such atoms of space, and to have a superposition also on the different ways they could be related to one another. So you would like to sum over the graphs as well. That's harder. That's harder, so the first two steps are mathematically well under control. The third step of making superpositions of the graph structure, there's people working on it, so it's not like we cannot do anything. Things can be done, but it's harder.
Some other question?
Especially if I said something that sounded, against the things you have heard before, I like to hear it. Or if some aspects of the initial presentation raised the curiosity of the students, I would also be happy to hear. Oh, we have a young student now asking questions. That's very good.
You mean myself,
yes.
Right? Okay, thank you. So Simone, how would you explain electron, for example, exactly in this scheme?
Sorry, how would you?
Electron, one single electron. So if I would like to imagine that, because now, if I understood correctly, you talk mainly about gravity itself only.
Yes.
So you have no fields, nothing inside.
Right.
So how they are coming in the game?
So again, without dynamics, the kinematical picture to describe that is that this graph, as you will learn tomorrow, gauge invariance imposes this graph to be closed. So every node, every link has to end in a node, or every edge has to end in a vertex. However, if you have loose edges, so they don't close to a node, that's where you can put matter degrees of freedom. Okay, so the kinematical picture is that you will see matter degrees of freedom as defects of this graph. So it's a technical answer.
But do they interact? I mean,
no, again, it was just a kinematical. Then, now you want to know how is the dynamics, but again, you see, it's the same question, because we would like that now the dynamics of these things are large scales, reproduces the Klein-Gordon dynamics, the Dirac dynamics, whatever it is. So what we're trying to do is to actually solve the question without matter first. So let's try to recover the GR dynamics first, and then we see if we can add matter consistently too. The only interesting results that concern the dynamics of matter, as far as I'm concerned, are results that show that, for instance, the ultraviolet divergence. So one thing that you would expect this scenario to give you is a better ultraviolet behavior. You would expect ultraviolet divergences of the matter interaction to not be there, simply because, you see, in a sense, it's very unnatural, no? The problem of UV divergences is because, you know, you're asking that they really hit in one point. So that clearly is a mathematical idealization. So clearly the problem of UV renormalization is due to our mathematical description and not to the physics of the problem. So the fact that there's a certain uncertainty, minimal uncertainty built in, unavoidable on where the interaction occurred, is quite natural, and it's quite natural that it solves this ultraviolet problem. But these are words. From these words to actual calculations, there's a bridge, there's a gap that we haven't bridged. So,
thank you.
In fact, my PhD thesis was called Towards the Photon in Spin Foams. And I'm still towards, you know.
I was wondering, how does it describe a principle of a cosmic censorship?
Very good question. So I could have mentioned that. So you see, cosmic censorship conjecture is that all singularities are hidden behind an event horizon. So this is the censorship. The singularities, we don't see it. And that's kind of like the spirit in which you say, okay, I don't need to address the question of is the singularity resolved or not, because I conjecture that all the singularities will remain behind some screen that will force me not to see it. So in this scenario, you will say that at the end of the evaporation of a black hole, there's some remnant. There's some remnant that cannot disappear, and so the censorship is still at play in preventing me from knowing what is the fate of the singularity, because there's a remnant. The remnant scenario has some technical difficulties, but it's something that people work on as well. So that could be. But actually, this launches me in telling you what is my favorite resolution of the problem of the information of a black hole, because you see, maybe, do you know what is the information paradox? All right, so this is a very interesting problem that also motivates the research in quantum gravity, is the fact that once I've thrown my, my worst enemy, or no, let's not be so mean, once I've thrown a chair inside the black hole will radiate gravitational waves. LIGO will not measure it because the effect is too small. You have to throw another black hole at the black hole before LIGO can see something. But once it has wobbled, it will settle down to a state in which it will be only characterized by its mass and angular momentum. But you see, the chair had much more information, because maybe the chair was spinning, but the chair is characterized by more than the way it's spinning and its mass. it has a shape. It has a lot of information. In fact, let's imagine I'm throwing this piece of paper inside the black hole. There's a lot of information, which I can't read because it's written in your funny language, guys. By the way, congratulations. I cannot understand a single word of your language. It's amazing. But it's very fascinating. You throw it in, you lose all this information. So, at the end of the evaporation of the black hole, what happens? Can we retrieve that information or not? So this is the famous puzzle of information, which animates endless discussion between theoretical physicists, motivates entire careers, and lots of fights and discussions, because there's no direct experimental evidence, so research is purely theoretical and based on the logic and ideas that people have. So for instance, one of the problems of the remnant scenario is that this remnant has to be very, very small, because the black hole will evaporate until it reaches the Planck scale, and so it's really, really small, kind of like this scale small, and yet it has to have all the information about all the things that went inside. So you have a lot of information in what looks like a very, very small space. But there are two resolutions of this problem. The first, so why is the black hole Planckian? Because its area is of Planck size. So at the end of the evaporation of this remnant, the area would be something like this really small number. But that's the area. One of the beauty of curved spacetimes is that they're not flat. So I can have an arbitrarily large volume inside such a small area. You don't have to make the mistake of thinking this is an Euclidean space, and therefore, if the area is small, the volume is also small. This is a curved space, and so it can be, think of it as, like when you're making a balloon. Like, the perimeter of your thing that you blow inside to make the balloon is very small, but then you can make a big balloon. Bring this one dimension up, small area can have big volume inside. That's one possibility. Another possibility, which I like very much, is what happens when you burn this piece of paper? Do you remember what happens when you burn this piece of paper? Where does the information go? It goes in the what do you say?
In the temperature around it.
So the temperature around will grow because I burned it. So the entropy will increase. But is the information lost? Increase of entropy does not mean that the information is lost. What it means is that information is degraded. Energy is degraded. So where is the degraded means that it's harder to access. So where does the information go? Well, if instead of being X, this thing was Y, when I burn it, the gas molecule excited by the photon emitted will have a slightly different trajectory because it was Y instead of X. So this information goes into the correlations between the air molecules that have been heated by the fire. So the information is not lost, but is now completely unretrievable, because if you want to recover what was written there, you will have to backtrack the evolution of all your gas molecules, and you cannot do that. Okay, so it's not. So one of my favorite idea, which is not mine, it's due to my colleague Alejandro Perez, is that the same thing happens in the case of the black hole, because you see this picture here allows you to play a same game, because the fact that we have many, many atoms is a problem to recover the smooth continuum limit, but it's also powerful because it tells you that just like in the atmosphere, atmosphere has a certain temperature, but is actually characterized by an humongous number of different states, which at the microscopic level are all different, but when I measure the temperature, they're all the same, right? That's the coarse graining. So here too, you can have an humongous number of different microscopic states, which all have the same macroscopic appearance of being flat classical spacetime. So that's where the entropy could go. Could degrade, the information could go into the correlations between the quanta of space and everything that has interacted with them at the Planck scale. So, but again, unfortunately, beautiful idea. We don't know how to compute. We have been trying with Alejandro to find a model in which we could compute this to see whether it works or not. It's just an idea I'm giving you. Don't take it as a solid result, because it's not.
Okay, so probably we will thank the speaker again. Oh, so maybe a last question.
At first, thank you for the great lecture. But just yesterday, I had a talk with one, I think, really clever informatician, and he said that our view of information is, in fact, not really well understood because, as you've...
what is not well understood, sorry?
Information as itself, because in the past, like he even talked about Aristotle, he said that it is something which is connected with, I don't know how to say it in English, but it was called helos.
What is helos?
Helos, it's like látka. That in fact it
Substanza?
Substance, yeah. But then it was transferred because of Latin language into materia, and today we think about it as a matter, and I think
we think of it as
a matter that we connected with matter,
with nature, with matter.
Sorry, matter, and so isn't it like this that what is in fact lost is just key to the information and not information as itself, because when we burn the paper, I think it doesn't matter that there are written some equations or just random...
No, but you can distinguish what was written. So the question is, should this information, the fact that the piece of paper was red or green, should this be lost or not? So in the way we formulate the laws of physics, we tend to stick to some principles. For instance, the conservation of energy. Things can be transformed, but not completely destroyed. So another principle is the fact that information is preserved. So why is this question of the black hole interesting? Because it might force us to revise this principle and say, no, it's no longer true. Or it might tell us that there are interesting ways, even though not obvious at first, in which this principle is still satisfied. But you see, the principle of conservation of energy, the principle of conservation of information, are things that are principles. Namely, we don't prove them, we use them to describe the world around us, and it's very helpful to have them. So that's why we take care so much about them, because they've been so powerful in bringing us where we are now, that you have to, when you want to give up an important concept like that, you have to worry that many of the things that we understand might be lost. So that's why you have to be very careful. So that's why people prefer to, in principle, solve this paradox by finding a way in which information can be preserved. But of course, it could be lost. Every time I open the door, over in the window, information is lost because there's air that goes out, air that comes in. So if I only look at the system inside, information is lost. So you might also say black holes are punctures into another universe, and so information is lost because it's going into another universe and I can never retrieve it. That exists also as an approach. So.
Okay, thank you.
Okay, so there's 8 hours, so let's thanks again.